We'll wait for 5 more minutes and then we'll start. So can we start now? Hello? Can we start now? Am I audible?
Yes, sir.
Okay. My screen is visible, right?
Yes, sir. It's visible.
Okay. Have you submitted the week 3 assignment?
Yes, sir.
So how was the assignment?
Easy, sir.
Easy, na? What we discussed, it was kind of similar, right?
Yes, sir.
Okay, so you were able to solve every question?
Yes, sir.
You have any doubt regarding the previous assignments?
No, sir.
No, na? Fine, okay. Okay then, well, we'll begin this this session. This is for the week 4 content, and this includes 2 lectures which is lecture 1 and lecture 2. Lecture 1 is the mechanics of oblique cutting, and lecture 2 is the measurement of cutting forces. So we have discussed last week about various methods to find the force using analytical model, using numerical model, using the finite element methods, modeling and everything. We have discussed about the various velocity triangle, how to find the relationship between the different velocities. We have discussed about the minimum power condition, how to get the value of phi for the minimum power condition, and the different using this strain rate relationship. So we have discussed about the various things. Now we will discuss in this lecture about, we will be discussing on the same thing, but we'll touch upon the different topics like the mechanics, the other force relationship, how to find force from the strains. This all will cover. Okay then. So first with the what is oblique cutting. So we have already seen in our previous lectures what is oblique cutting. Oblique cutting is basically a type of cutting in which when the chip does not flow in the orthogonal plane. I have already told this, what is the difference between orthogonal cutting and oblique cutting, and how does the chip flows in the orthogonal plane and on the normal plane. This has been discussed already. So we are just revising it. Okay, the oblique cutting is that cutting in which the chip does not flow orthogonally. It flows on an other plane. It could be any other plane. So this is basically the definition of oblique cutting. Now we will see, because of this oblique cutting, now the angles which we have studied, which are the rake angle, the orthogonal rake angle, the normal rake angle. So these are actually not the true rake angles, because these are the angles which are on a particular plane. For example, on the orthogonal plane we have orthogonal rake angle, orthogonal clearance angle. On the normal plane we have the normal rake angle, normal clearance angle. But actually, does the chip flows in this plane only, or there is some other plane where the effective chip flowing is there? So we will see today at what plane or what is the actual angle to be considered while calculating the true rake angle. Fine. Now see, whenever the chip flows, there is a deviation in the chip. So the chip deviation is mainly because of three reasons. One is because of the inclination angle effect, one is because of the cutting edge radius effect, and third is because of the secondary cutting edge effect. Okay, we'll go this one by one. How does this particular effect changes the chip? So first is inclination angle effect. We already discussed what was inclination angle. How does inclination angle, because of inclination angle, the chip does not flow on the orthogonal plane, it get deviated by an angle I. We know that inclination angle is I, right? Inclination is I, which is inclination angle. So because of this I, if the chip has to flow in this, for example, if the chip has to flow in this plane, ZO, which is the orthogonal plane, it does not flow in ZO, it flows in ZN, which is the normal plane. So this by the angle which it deviates from the orthogonal plane to the normal plane is called the inclination angle in a simple sense. So one of the reason of the chip deviation is inclination angle, which we have already discussed. So this is reason 1. Second is reason 2, which is the cutting edge radius effect. See, whatever tool we are seeing basically in the macro cutting, in our conventional tooling, the tool we considered while we derive the merchant theory also, or merchant forces also, we assume that the cutting edge or it is perfectly sharp. We assume that the cutting tool is perfectly sharp like this, right? But in actual, the cutting tool has some radius. It is not perfectly sharp. It is having some radius like this. This is perfectly sharp, pointed, and this is having some radius r, right? Because of this radius, there comes an difference in the geometry, how the chip flows. Entire geometrical calculation change, and we have some other angles of some other planes which come into contact. So because of this existence of this cutting edge, which have some radius, which 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 result in the deviation of the chip flow. So this is the second reason. Third is the secondary cutting edge effect. See, we already have discussed that for a tool there are two edges. This was the tool, right? This was the tool. This was the tool. So this was the primary cutting edge, PCE, and this was the secondary cutting edge, SCE. So the major cutting was done using PCE, the primary cutting edge, but we also had SCE, which is the secondary cutting edge, which also contributed in the cutting process. But however, as the major cutting was done through PCE, we almost ignored this SCE because the cutting through SCE was very minor. But in actual case, the chips, because however SC is cutting, so if cutting is there, then chip flow is also there, right? So if chip flow is there, then chip will come out. So because of the chips which are coming from the SC, secondary cutting edge, will obstruct the chips coming from the PC. For example, I'll just draw it once. See, this is major cutting edge, PC, and this is secondary cutting edge, SCE, SCE and PCE. So after cutting here, for example, some chips are coming. See, some chips are coming. It has some direction. It has some direction. Now from SCE also small chips or some minor chips are coming. These are coming. See, coming. Now when this chip will come in contact with this chip, for example, it's coming in contact with this chip, the primary chips, then it will deviate the direction of this primary chip so that this chip will not move on the plane it was supposed to be. It will get deviated to some other plane. See, it is getting some deviated. It is getting deviated. So this deviation, this moves the chips to some other plane. 1 second. There is someone to join. Okay. My screen is visible, right? Hello?
Yes.
Okay. So what I was telling, ki the chips are coming from
Deviated chip.
the chip which are coming from primary cutting edge. Also some minor chips are coming from the secondary cutting edge. So because of that minor chips, it pushes the primary chips and it deviates those chips from its original position. Because of that, chip deviation occurs. This is as simple as understand that if someone is running in the ground and some other person comes from other direction and pushes the person, then that push will deviate the person from his or her original path. This is as simple as that. Okay, so because of these three reasons, there is a majorly chip deviation. One is inclination angle, one is the cutting edge radius effect, and one is the secondary cutting edge effect. Fine. Now, if chip deviation occurs, then the angle will also change, because now it is coming to a new plane. So we have calculated the rake angle, side cutting edge angle, and the clearance angle on a particular plane, on a particular normal plane, on a particular orthogonal plane. But now we need to calculate this angle on the new plane. What are this new plane? This new plane is those plane or that plane in which actual chip is flowing. And why the actual chip is flowing in that plane? Because of all this effect: inclination angle effect, cutting edge radius effect, and secondary cutting edge effect. Now we need to search that new plane at which the chip is actually flowing, so that we can calculate all the angles, right? So this was the concept behind why we are calculating the new angle. For example, the normal shear angle, effective shear angle, effective rake angle, true rake angle. Why there is a need of calculating again if we have already calculated in the normal plane and orthogonal plane. So this is the reason, because chip deviates into that particular plane. Now coming to true and effective rake angle. So why this true and effective rake angle comes into picture, which I have already explained, because the chip is flowing in other plane. So if it's flowing in other plane, so that plane have its rake surface. So for that rake surface, we need to find the effective rake angle, right? So the angle between the rake surface and that plane will be the definition of rake angle remains same. The definition of rake angle remains same. It's how it's depend upon at which plane you are looking at. So when we are looking at this true plane, it is called the true rake angle or effective rake angle. Now see, now I'm not going into the derivation of the effective rake angle because that sir has already covered. I'll just give the formula and explain how the formula should be used. The formula of the alpha E is the effective rake angle, or it's also called true rake angle. See, sine alpha E is equal to sine I. So I is the inclination angle into sine, you can say it gamma C, NC, whatever you want to say. Like this gamma C or NC or eta C, whatever it is, eta C, it's called the chip flow angle. It is that angle at which the chip flow from the given plane. Right? So sine alpha E, which is a sine effective rake angle, equal to sine of inclination angle plus sine of chip flow angle plus cos of inclination angle into cos of chip flow angle into sine of normal rake angle. We have normal plane also in which the chip flows, right? Now from orthogonal, see, it is like this. We have orthogonal plane. This is Z0. We have then normal plane Zn, and then we have some effective plane or true plane, which is Ze. So the transition of chip is from Z0 to Zn and then Zn to Ze. So this Ze is the actual plane where the chip flows because of various chip deviation effect we have discussed. Chip flows, actual chip flows, right? So this angle is what? Inclination angle, the angle from the Z0 orthogonal plane to the normal plane, right? Now, so this is the formula. This is a very important formula. We need to remember it because like so many numericals are being asked from this formula. Directly we need to use this formula and find the relation where we know I is the inclination angle, NC is the chip flow angle, the angle at which the chip flows from the normal plane to this chip true plane, and alpha n is the normal rake angle. Fine. Now this is the formula, but there is a special case. What is special case? When I, which is the inclination angle, it become equal to the chip flow angle, means that means the angle by which chip deviates from the orthogonal plane to the normal plane, at the same angle the flow angle is there for the chip. So if it is same, then I is equal to NC, right? In this case, what we'll do, we'll put I equal to NC, and the formula we will get is sine alpha is equal to sine square I, because I and NC are same, right? So it would become sine square I plus cos square I into sine alpha n. So you just need to remember this formula, and in some special case you can put I is equal to NC and find this formula. This is very simple. So I think it is clear. Can I move to next slide?
Yes, sir.
Okay, fine. Now see, now up you are going from orthogonal plane to normal plane, then to effective plane, then you will have different shear angle also, right? Shear angle, you know what is shear angle. For example, this is a tool. In normal I am saying, normal tool. This is a tool, and see, this is a workpiece. This is a workpiece, right? So, and chips are flowing like this. Chips are flowing like this. Take to the plane at which the chip is getting sheared. The plane at which the chip is getting sheared, that is called this is called the shear plane. Shear plane, right? And the angle of that plane with the horizontal is the shear angle, phi. Psi. Okay, so this is basic definition of shear angle. Now we'll see how different shear angle exist. So this derivation and all are already been covered in the class. I'll just revise the formulas and I'll teach you how to use them while solving the numericals. Now, so one is normal shear angle. What is the normal shear angle? It's the angle from the shear plane to the plane which contain the newly found work surface in a plane which is normal to the cutting edge. See, I'll show you. fine. One second. Yeah, so basically we know that one formula, right? This formula, 10 phi is equal to r cos alpha upon 1 minus r sin alpha. For orthogonal cutting, for normal condition, we know that this is a very famous formula. 10 phi is equal to r cos alpha upon r sin alpha. But when you're talking about the normal shear plane, normal, then this phi becomes phi n. See, it becomes phi n, which is the normal shear angle, and this r remains the same, which is the chip thickness ratio, and the alpha also become alpha n, which is a normal rake angle. So this formula changes in the normal plane, just the everything remains same. The shear angle remains same, the definition of shear angle remains same. Only if it is taken on the normal plane, the angle become normal shear angle, and the rake angle become normal rake angle. Fine. Second is the effective shear angle. Now what happens? You are going from orthogonal plane pi o to normal plane pi n to effective plane pi e. So you are here to here I, then you are again moving. So this displacement from orthogonal plane to normal plane to pi, now you come to pi. So at pi e we found the effective rake angle. Similarly we'll find the effective shear angle. But here you need to the derivation for this is already given. There is a slight change in the formula because some other obstructions also come here. For example, here in normal plane it was same of the orthogonal plane, but in the effective plane there comes another ratio which is called the chip width ratio. It is very similar to the chip thickness ratio. Chip thickness ratio was what? T by Tc, where Tc is the chip thickness and T is the uncut chip thickness. Similarly, there comes a term called Rb, which is the chip width ratio, which is Rb is equal to B by Bc, where B is the width of the chip and where B is the width of the uncut chip. So this formula comes into picture, where 10 phi e is equal to RT Rb cos alpha e upon RT Rb sin alpha e. Alpha is effective rake angle, which we have already discussed in the previous slide. So this formula you need to consider, you need to remember of the normal rake angle and the effective rake angle. Okay. Can I move to next slide?
Yes, sir.
Okay. If you have any doubt in between, please feel free to ask. Anytime you can stop me and ask the doubt. Okay. Okay. Now coming to very important part in any process, whether it is machining process or non-machining process, we are always concerned about the forces, because these forces are one of the factors which determine the stability of any process. We always want the right force to act on right direction and on right amount, so that we can stabilize our process and get more out of it. So basically in oblique cutting we have three forces. One is the feed force, one is the radial force, and one is the cutting force. So I'll explain this using the example of a turning process, single point turning process. See, this is the workpiece. See, this is the tool. This is the tool. This is the tool. This is the workpiece, right? So we are turning it. So this was first the workpiece diameter. This diameter has been reduced to this. It has been reduced from D1 to D2. Now see what happens in turning process. The workpiece rotates. See, this is the workpiece and it is rotating by an spindle speed ns. See, you can see n, and tool is moving on this direction, this direction, by a feed rate f, right? So we have already learned कि in case here the major cutting would be this rotation, because the workpiece is rotating, and the minor cutting would be the feed motion. The generatrix would be the workpiece motion, which is the primary motion, and the directrix would be the feed motion, which is the tool motion, right? This all we have already discussed before. Now see, when tool is cutting, for example, see, I'm drawing it here. This is a workpiece. This is a workpiece. This is rotating, right? This is rotating, and this is the tool. This is some tool which is reducing the diameter of the workpiece. This is the tool, this is the workpiece. The workpiece is moving in this direction by speed n, and tool is continuously feeding in this direction with a speed of feed rate f. Right? So if we'll consider a point, for example, let's consider this point. See this point. To this point we have a force F here, feed, which is called feed force because tool is feeding in this direction, which is denoted by FF. Now if the workpiece is rotating, so there might be a force which is cutting the workpiece, which is the cutting force, and that force is tangent to this this workpiece, which is this is like this FC. So we got two force. One is the feed force along the tool feeding direction, and one is the cutting force, which is tangent to the workpiece, which is responsible for the cutting of the workpiece. And because of this developed thrust, there would be another force also, which is radial to the direction of this cutting or of this workpiece, which is like this FR, which is called the radial force. So we got three forces: cutting force, feed force, and radial force. Now to find the net force, we need to find a total force, which is called the resultant force, and which is equal to under root of ff square plus fr square plus fc square, because these are three mutually perpendicular forces, right? So if we need to find the vector sum or the resultant force, we need to take the square root of this forces, square of the square roots. So this is feed square force plus radial square force plus cutting square force. So this is the resultant force. We need to find this force for the resultant force. So I think this is okay. Can I move to next slide?
Yes, sir. Sir,
Yes.
One question is there.
Yes.
Sir, if you want to if you want to vary the diameter more,
Okay.
so you want to cut more diameter, so D2 will be more or less. So there will be another motion to what we can say, to push the cutting tool more inside.
Right.
So that motion is there. So there will be another force, no?
No. You want to what? Reduce the diameter more.
Yeah.
No.
If I don't want to keep the diameter constant throughout the workpiece.
So here diameter is not constant. You want a taper, right?
Yeah.
No. That would be same. The forces acting would be same. The direction of force can change. This is straight turning. There are taper turning also, like this. You'll not get this constant. You'll get like you're saying like this, right? Like you are saying like this diameter is varying, right?
Yes, sir.
Okay. So here also the same forces will act. The feed force, the radial force, the cutting force. However, there can be changes in the direction of the forces. No extra force will be introduced. Hello.
Okay, sir. Okay,
Fine.
sir.
Fine, na?
Yes, sir.
Okay, fine. Now we'll see a small video about the forces which we have learned. Please watch it.
In today's session, we will learn about tool dynamometer. This method is used to determine cutting force. Here the forces involved in oblique metal turning process are shown in figure. Here FF is the feed force or axial force which act in horizontal plane parallel to axis of workpiece but in opposite direction to feed. Here FR is the radial force or thrust force which act along the radius of workpiece. It is the smallest force acting along the axis of tool. Next is FC, which is cutting force or tangential force which act in vertical plane and it is tangential to work surface. It is the largest force in cutting operation, and FCN is the cutting normal force. Here the resultant force for oblique cutting system is given by the formula R is equal to under root FF square plus FR square plus FC square. For orthogonal cutting system, the formula is the resultant force is given by R is equal to under root FF square plus FC square. Now cutting force is depend on workpiece material, depth of cut, feed, tool geometry, cutting fluid. So here we have two basic cutting processes, that is orthogonal cutting and oblique cutting. In orthogonal cutting, The cutting face of tool is perpendicular to direction of feed and it is known as two-dimensional cutting. Where in oblique cutting, cutting face of tool is inclined at angle less than 90 degree and it is known as three-dimensional cutting. The tool life in orthogonal cutting is less, wherein tool life in oblique cutting is more.
Okay, so we have seen a small video about the various forces and the direction in which they are acting. So we know the orthogonal cutting, we consider it as a 2D cutting type because we draw the merchant cycle considering it to be a orthogonal cutting, so we can represent it graphically on a 2D figure something. But oblique cutting is a 3D cutting process. Therefore in oblique cutting we have one extra force which is called the radial force. However in the oblique cutting we have only two forces to find the resultant. Okay, now we have some basic method to find the forces, like we have seen different method to find the forces, but also the forces can be find through like we know the forces, the very important system or instrument to find the force is a dynamometer, which gives the force like in x direction, y direction and z direction. However, dynamometer also gives the value of torque, but we as per now we are constrained about the forces only, so we'll talk about the forces. For example, a dynamometer gives a three force fx, fy and fz, so we can find these three forces using a dynamometer, but we can also find the forces using other method, basically using the strain gauges or other methods which with the help of strains can give the value of forces. So that instrument gives the value of strains by measuring the resistance or any other things, internal process, but and we know that how that strain is related to the force, and so that we can find the force from that value of strain. So now we will look some of the methods, right? So first is axially loaded member. See, when you load the any member axially, for example, we have this circular bar or something, cylinder type, right, and whose length is L, whose area is A, and whose Young's modulus is E. And now I am stretching this material using a force F. Okay, using a force F. So we already know कि when we stretch something by a force, then the strain which develop for the axially loaded member is F by AE. This is a well-known thing, I think. The strain developed in the axially loaded member is F upon AE, right? This we can find also because, see, we can prove also this strain is, what is strain? Strain is the stress upon E. This is known, right? From the stress strain curve we know this is strain, this is stress, and this is E. So stress upon strain is E, right? So from here the strain is stress upon E, and what is stress? Force upon area, to F upon AE. So the formula of strain is F upon AE. So for a axially loaded member, if you know the value of strain, and what is strain? Strain is change in length upon original length. If you know the value of strain, and you already know the Young's modulus value, and the area is what? Pi by 4 d. If the diameter is d, then what is d? Pi by 4 d square area for a particular instance. Then you can directly find F. So from knowing the material property and calculating the strain, we can find F, which is the force. This is one of the method of finding force. See. So here what we have done, this is the axially loaded member which is having an force F, axial force F. Now we are stretching the forces, stretching this member. So, and you can see some strip of material been attached to this member. These are the strain gauges actually. See, 1, 2, 3 and 4. See, So we have strain gauges attached in two direction. Is in the longitudinal direction, which are 1 and 4, and two are on the perpendicular direction, which are 2 and 3. It is not looking like that, but actually it is placed at that direction only. So for 1 and 2 it is for 1 and 4 it is on the same direction of the force, right? Force is also acting here longitudinally, and in this direction only we have this 1 and 4. So the formula of strain would be same, F by AE. But when we'll see 2 3, this 2 3 direction is transfers to this axial direction. So we cannot use the same formula of the strain for 2E. So then there comes a concept of Poisson ratio. Do you know about the Poisson ratio? Hello?
No, sir.
You don't know? Okay, it is a very basic thing, but I'll tell you once again. See, please listen to it very carefully. Na? See, for example, we have a material whose length is L, right? We have a rectangle or something whose length is L, or anything, cylinder, rectangle, anything, right? Consider it as a cylinder. Length is L and diameter is D, and we are pulling it in this X direction. This is X direction, we are pulling it. This is clear, right?
Yes, sir.
So after some time, one second. Okay, so after so after some time, if we are pulling it, it will stretch, right? So it will somehow become like this. See, its length will increase, but its area will decrease, right?
Yes, sir.
Like this. So now the length become L dash and area become D dash. So L dash is greater than L, but D dash is less than D. It is clear? Okay.
Yes, sir.
Fine. So we can see, so the strain developed in X direction, epsilon X, will be what? Change in length upon original length. So which is equal to L dash minus L upon L, right?
Yes, sir.
Also, there is a change in the length in the Y direction, this direction, D direction, which is epsilon Y, which is equal to change in D upon original D. So change in D is how much? D dash minus D upon D. So this is a very interesting thing to note, कि when you are applying force in one direction, you are applying force only in X direction, right? But
Yes, sir.
so if you are applying a force in some particular direction, then the change in dimension should be there only in that direction. But however, the dimension is also changing in the next direction also, or the perpendicular direction also. So this is due to some effect which is called you can just remember, this is because of some ratio which is called the Poisson's ratio. This Poisson's ratio is that ratio which enables the change in direction in the transverse direction, right? So because of that, a ratio is originated which is called mu or u, or which is called the lateral strain upon longitudinal strain. If you don't know, please note this formula. Later I'll write it properly. Wait. So this I'll write, wait. The Poisson's ratio mu is lateral strain. Lateral strain means the perpendicular strain. In this case, it is a y direction upon the longitudinal strain which is along the direction of the force, and here come a negative sign. You can see the negative sign.
Yes, sir.
Can anyone tell me why I have written this negative sign? Can anyone tell me that? Do you have any idea? You can guess also. No idea?
No, sir.
Okay, see, we want the ratio to be positive, right? So you have seen here कि this is positive because length is increasing. The del L
Yes,
is
sir.
L dash minus L. So L dash is greater than L. This is positive. So this ratio is positive. This epsilon x is what? Epsilon x is longitudinal strain. Why it is longitudinal strain? Because it is along the direction of the force. The strain which is along the direction of the applied force is called longitudinal strain, and the strain which is perpendicular to the direction of the applied force is called lateral strain. This is clear, right?
Yes, sir.
Along the force is longitudinal, perpendicular to that is called lateral or transverse, anything, lateral strain. Okay, so in this longitudinal direction the length is increasing, so this is positive. But in lateral direction this diameter is decreasing na. So if diameter is decreasing, then this del d should be negative. D final minus D initial, so D final is less than D initial na. So it is change is negative, right?
Yes, sir.
So change is negative, then this epsilon y will be negative. So if we'll put here negative upon positive, the ratio will come negative, right?
Yes,
To
sir.
avoid that negative ratio, we multiply it with the sign negative, so that negative will become positive. Right now?
Yes, sir.
Understood?
Yes, sir.
So this is the concept of Poisson ratio. The Poisson ratio, it comes into picture because of the strain developed in the lateral direction. Fine? Can I rub it?
Yes, sir.
Okay. Fine. Now see, similarly if the force is in this direction, this F is in this direction, and in this direction we have two strains, two strain gauge 1 and 4, and perpendicular to this we have 2 and 3. The value of strain for this 1 and 4 are equal, which will equal to what? F upon AE, right? But for this 2 and 3, these are the lateral strain. So we know कि this Poisson ratio is equal to minus of this longitudinal strain epsilon x upon lateral strain epsilon y. Sorry, I have written opposite. It's a ratio of the lateral strain upon longitudinal strain. So this we know longitudinal. So the lateral strain can be found. So E lateral is minus mu times of E longitudinal. This we can write. Hello?
Yes, sir.
So this is very easy na, because Poisson ratio is negative of lateral strain upon longitudinal strain. The lateral strain is what? This into this.
Yes, sir.
So then minus V times of what is longitudinal? Longitudinal is this epsilon 1 into epsilon 4, which is what? F upon AE. So the lateral strain is what? Minus mu F upon AE, right?
Yes.
So this way you can find the forces value in whatever direction you want, using the whatever strain gauge in either in the longitudinal direction or in the lateral direction. So this is very important concept about the Poisson ratio, which we should know because it is very useful in calculation of the strains and stresses. Okay, So this is one of the method of calculating force. Now we'll go to another method. This method is clear, or you are having any doubt?
No, sir.
If you want to ask anything about, you can ask. Okay, now we are going to next method, which is called the cantilever beam method. See, in cantilever beam method, what we do, we for any cross section, we for any material, it can be a square or a cylinder or anything. We keep the strain gauges at the what to say, at the cross section, and we, for example, if it is a square, okay, it is a square which is having a width of B and a thickness of H, right, this, and we keep the strain gauges here at the cross section. These are the strain gauges, and we connect that strain gauges such that they form a Wheatstone bridge, and using the, see, every material have is the resistivity. So when you apply the current, so some resistance will be developed. We know that na, R is equal to we have learned this rho L by A. You know all this? This is a very simple physics.
Yes, sir.
है ना? So R, when you every material have the rho, and when you apply the current, then some resistance is developed. So because of the resistance, we convert the resistance into the change in length, and because of change in length, we get the strains, and from the strain we will get the force. Very simple. You apply current I, find there would be a resistance. Resistance means there would be some change in length, del L by L. This would cause the strain, and from strain you can calculate the force. Right. So similarly happening here, you are applying current, then because of change in length, some strain is developed, and from the strain we can calculate the force. So I am directly using the formula. Since this is a very symmetric structure, the value of every strain will be same, which comes out to be 6 FL upon EBH square. See, B and H are thickness. For example, if B is equal to H, then it will become B cube. Very simple, right? So this is one of the method which is called a cantilever beam method, in order to find the forces. Actually we are finding the strains, and the formula, and equating it with the force formula, we are able to find the strains. Fine?
Yes, sir.
Okay, now we'll moving on to next method, which is the ring method. Similar to this cantilever beam method, we have a ring method in which the strains are applied on a ring, and it's subjected to a force. So because of the ring, so we have different, like we have a 360-degree domain, right? 360-degree domain. So in 360-degree domain, we can apply the force at anywhere, at 90 degree and 120, at 60, anywhere. So basically for every angle we have a different formulas, a different calculation, but the most common calculation is for the 90 degrees. So for 90 degrees, what the strain we developed is plus minus 1.09 into F into R upon EBT square, where B is the width and T is the thickness. B is the width and T is the thickness. Right? So just remember this formula, ki for 90 degree, what is the formula for the this? Sir has taught all these, right? So just we'll solve the numericals. If you don't have this formula, just write it. I'm going to the previous slide. Please write the formula in a page, so that while solving the numericals, it would be helpful. See, you can write all these formulas for 1 and 2. E1 equal to E4 equal to F upon AE, E2 equal to E3 equal to minus mu F upon AE, for cantilever beam is this strain is equal to 6 FL upon EBH square. B is the width and H is the thickness or height. Okay, and for this method we have the formula is plus minus 1.09 FR upon EBT square. So this basics formula you should know, so that while solving numerical it will be very easy for you to solve. Now coming to the one more method. Yeah, do you have any doubt?
No, sir.
Okay. Now one more method is that the determination of cutting forces through measurement of elastic deflection. Now what happens, for example, there is some cantilever. Cantilever is a type of beam in which one end of the beam is fixed. See, this is any beam. It can be a cylinder or a rectangle, anything it can be. See, its one end is fixed, it cannot move, it is fixed, and one end is free, which can move. So when I apply a force, for example F I have applied, right? This is visible, right?
Yes, sir.
Okay, now you see, it is very interesting. I think you might have seen this in your strength of material.
Sir, actually, I have these types of supports and beams in engineering mechanics first year course.
Then you might have seen this, no?
Yeah.
So see, this is the beam and this one force is acting. So because it is free and it is fixed, so there will be some deflection. So this beam will become like this now. This beam will deflect, है ना? And it will become like this, right? So there will be some deflection like this. It has come from here to here, which is equal to delta. And this delta value for a cantilever standard value is FL upon 3EI. Wait. The standard value is this deflection is equal to FL cube upon 3EI. So if we know the value of deflection, then and this how it is a well derived formula. I am not going into derivation. It is a well derived formula. Ki how there are different methods to derive it. You can do this, you can see it. And this deflection for a cantilever of a normal beam is FL cube upon 3EI, where I is the moment of inertia and which have different values for different cross sections. Okay. Now, if you know the deflection, then similarly you can find the value of force. This is very easy to find the value of force now. See, FL upon 3EI. It's very simple. Now, our last topic for today is gauge factor. So what is gauge factor? See, what happens. See, when you apply any current or any force to a material, right? So there is some inherent resistance or inherent resistivity of a material. Because of that current, as I already discussed, because of that current, there develop a resistance. So the development of the resistance is basically because of the change in the length. So this, for example, this strain can be measured. If change in length is occurred, means there is a strain developed, right? Because strain is a change in length upon original length. But actually what is changing is the resistance value because of the application of the current. So this, from the change in resistance, you are getting a change in length. So this is a resistance and this is a length. Okay, so this is interconnected. This you are getting because you are applying I current, and from this is strain, you can get the force. So this conversion has to be taken care. This conversion, because you need to convert this resistance chain into length chain, right? So that is done, or that is calculated using a factor which is called a gauge factor. So gauge factor is what? This chain resistance upon the strain, which is what? Del L upon L. So from you, after calculating strain, we can find the stress, and from there we can find the force. So this is one of the very important factor to calculate the strain using the chain in resistance from a the strain gauge or wire something. This is fine.
Yes, sir.
Okay. So now our theory part for today class is completed. Do you have any doubt before we move to the practice session?
Sir, in the ring formula,
Yeah.
why it is plus minus both?
Actually, see, when you are talking about the circle, right? When you're talking about the circle, 90 degree, so you can 90 degree you can calculate in the, like this also, in the positive direction, and 90 degree you can calculate on the negative direction also. Hello.
Yes, sir. Yes, sir.
Like here, to calculate 90 degree, you can calculate here also 90 on positive side, and also this is also 90 na, on
Yes,
negative
sir.
side. So you can calculate on both side, on the positive side also, on the negative side also. That's why it is plus minus it is given. Okay,
Okay,
fine.
sir.
Okay.
Yes, sir.
Any other doubt to anyone? If not, then we'll move to the practice session. So
No doubts.
shall we move? Okay, fine. So we'll move to the practice session. Before that, please bring a copy and a pen and this calculator so that you can also solve. Because this session is mainly for your solving. I know you know the formulas, you can solve the assignments, but this is mainly for you to solve and practice. So anyone who is not now and will be looking to the video later on also, please don't just see the solution. See the question. I'm giving 5 minutes for every question so that you can solve it and then check whether you're done right, or if you're not able to solve, you can match the solution. Okay, fine, then we'll start the practice session. Okay, so this is the first question. In an oblique cutting process, the inclination angle is, see, I always say, before solving the question, just write what is given so that it will directly feed you what has to be done. So inclination angle, what is inclination angle? I is 5 degrees. Chip flow angle, what is chip flow angle? NC, which is 6 degrees. Effective rake angle, which is what? Alpha E, which is 8 degrees. You need to find the normal rake angle, alpha N. So, do you know the formula for this? Hello? Do you know the formula for this?
Yes, sir.
Can you tell me?
That sine one formula, na, sir?
Sine alpha E is equal
Alpha
to
E
sine
sine
I sine
sine
NC
NC
plus
plus
cos I cos NC into sine
Sine.
alpha N. Everything is
Yes.
given. You need to find alpha N, right?
Yes, sir.
Can you find it?
Yes, sir.
Please find it and tell me the answer.
Yes, sir.
Please solve it. Take your time, solve it.
Sir,
Yes.
sir, answer is 7.54.
Yeah. Yeah. Very good. Answer is, so what we have done here, we have just put the values. Sine of 8 degrees is equal to sine of 5 into sine of 6 plus cos of 5 into cos of 6 into sine alpha n. So on solving, the alpha n value is how much you got? 7.54, right?
Yes, sir.
This is absolutely right. 7.54. Okay, can we move to next question?
Yes, sir.
Okay. Now the second question. In an oblique cutting, the chip thickness ratio, which means R, right? RT, is given 0.55. The chip width ratio, which is RB, which is given 1.55. Effective rake angle means alpha E is given 6 degrees. The value of effective shear angle, which is epsilon phi E, you need to find. You know the formula of this? You know the formula of this? Hello?
Yes, sir.
I have taught na 10 phi E is equal to how much?
Uh,
RT into RB cos alpha E upon 1 minus RT into RB sin alpha E. Something like this. है ना? For the normal, there was a formula for the normal shear angle and formula for the effective shear angle. Right? Hello?
yes, sir.
So this formula you can use, right?
Yes, sir.
Please use it and solve and tell me the answer.
Yes, sir.
10 phi E equal to RT is how much? 0.55 into RB is 1.55 into cos alpha is 6 degree upon 1 minus 0.55 into 1.55 into sine 6 degrees. Please solve it and tell me the formula answer of for phi E.
Sir, 42.946.
Yeah. On solving this 10 phi E, we will get 0.93.
9307.
Yeah. Then phi will be around how much?
42.946.
Something like this, है ना?
Yes, sir.
Okay, it's right. Now we'll go to third question. A straight turning tool has a side rake angle. Side rake angle means alpha S is 12 degree, and a principal cutting edge angle means gamma P is 65 degrees. For achieving orthogonal cutting, find the maximum rake angle. You know the formula for maximum rake angle? Alpha max I have taught in the first class. It is under 10 alpha max is equal to 10 square alpha S plus 10 square alpha B. Alpha B is a back rake angle. You know that?
Yes, sir.
You know, right? So now we have alpha S, but we don't have the back rake angle.
90. 90 minus alpha.
No, 90 minus alpha is not that back rake angle. That is the relation between the side cutting edge angle and principal cutting edge angle. If you want the side cutting edge angle, then you will do 90 minus 65 to get the side cutting edge angle. But alpha S and alpha B are different. So there is a formula. You know the relation between. I taught a formula which is says the conversion from the orthogonal rake angle 1. Tan I is equal to tan alpha b sin gamma p minus tan alpha s cos gamma p. This I taught in the first class. You know this tool conversion system when I was teaching. This is
Yes, sir.
this came in your first assignment or second assignment. I don't know. Just revise it. You'll remember. Don't worry. It's simple. Right. So this is the formula. Hello.
Yes, sir.
Now can you solve it to get the value of alpha b?
Yes, sir.
Try once. There's one thing you need to understand to solve this. Rest it is easy.
Sir, here it is not given included angle.
This I is the inclination angle, right?
Yes.
See, this is the trick. This is orthogonal cutting. It is given, right?
Yes.
Yes, sir.
Or in orthogonal cutting, I will be 0.
Yes, sir.
So this is 0. So this should be 0 equal to tan alpha b into sine of 65 degree minus tan 12 into cos of 65 degree. Please find the value of alpha b from here. Now you can do na.
Yes, sir.
This was the trick because for orthogonal cutting I is 0 na. So you have to just put the value of I to be 0. Nothing else. So please solve it.
Sir, 5.66.
How much? 5.66 is the value of
Alpha b.
how much you got? 10 alpha b.
Tan alpha b 0.09911.
Okay, 0.099. है ना?
Yes,
So
sir.
you got 10 alpha b like this. So what will be the value of this? What is the value of alpha maximum from this formula?
Yes, sir. Wait.
10 alpha max is equal to under root 10 square alpha s plus 10 square alpha b. Now you know alpha s and alpha b both. 10 alpha b you know, na? No. Now just put it, square it and add and find the formula. Find the solution. 10 alpha b is right, 0.099.
13.17.
13.17 is the value of this, na? Maximum rake angle.
Yes.
Yeah, it's coming around, alpha max is coming around 13.2 something. Yeah, right. Fine. This is the answer. The only trick in this question was that you need to remember first of all this one formula, second this formula, and you should know for orthogonal cutting I is 0. Rest it is very easy. Okay.
Yes, sir.
Can we move to next question? It is clear.
Yes, sir.
Okay, then we are moving to fourth question, which says in oblique cutting process the inclination angle. Then we'll write it I is see you develop this habit of writing what is given. So what is given? I is given 8 degrees. Chip flow angle which is NC, which is given 6 degrees. Effective rake angle which is alpha E, which is given 8.5 degrees, right? You need to find the normal rake angle alpha n. This similar type of question we have done, na?
Yes, sir.
Just apply the formula. What is the formula?
Sin alpha E
Sin alpha
equal to
E.
sin I sin NC
Huh?
plus cos I cos NC sin alpha M.
Find the value of this then. Solve and find, please.
Sir, 7.776.
Alpha n value, na? Yeah.
Yes, sir.
It is coming to be around, yes. 7.78 out, yes. Fine. Okay. It's fine, na? Can we move to next question? Hello?
Yes, sir.
Okay. See. Now it is given in an oblique cutting. The feed force and radial force are this much. So how much is the feed force? FF is 300 Newton. And the radial force FR is 200 Newton. And the diameter is there. The diameter is given around 150 mm. The spindle speed, which is N, is 1200 RPM. RPM is revolution per minute. And total force on the cutting is, total means resultant force, which is R, which is 540 Newton. है ना. You need to find the power developed. You need to power in kilowatt. Can you solve it? Just tell me by looking it.
Sir, third force.
See, total force is given na.
Yes, sir.
You can calculate the third force from
We
here.
can find. Yes, sir.
So basically,
Under root square.
yeah. So basically, you try for 5 minutes, then I'll solve. Whatever you can try how to calculate power. Just think of yourself which force will be used to calculate power and how to calculate power. Just try, then we'll solve it very properly after 5 minutes. You just try once.
Okay, sir.
Have you got answer?
No, sir.
Are you understanding how to solve?
No, sir.
Okay, let it be. I'll solve this question. You see, okay? I'll just solve the question. You'll get an idea how to solve. How to approach this type of questions. See, what is there? It has asked to find the power, right? Hello?
Yes, sir.
The power is always equal to cutting force into velocity. This you need to know. Right? And
Yes, sir.
this power, it is asked in kilowatt. Kilowatt is what? Kilojoule per second. So you need to find the value of force in Newton and value of V in meter per second. This you need to understand. This is the first step. Okay? Now,
Okay.
first we will find this. This we need to know. This we need to know. This we need to find. Now, we'll find the value of first Fc. We know R equal to under root ff square plus FR square plus FC square. We know this, right?
Yes, sir.
R value is how much given? 540.
540.
So 540 equal to under root FF is 300 square plus FR is 200 square plus FC square. So we can find
Yes, sir.
FC from
Answer
here.
is four.
How much FC?
Yes, sir. FC is 401.99
So FC
or
is
402.
FZ is around 402.
Yes, sir.
402 Newton. FC we have got. Now we just want the value of V, which is the cutting velocity. So V is how much? V, the value of V is pi dn. Hello?
Yes.
You know, you knew this, the value of V written as pi dn?
IDN by 60.
Yeah, pi dn is in meter, this is in per minute. But if you want in per second, we will do by 60. Right?
Yes, sir.
Okay. Now just find pi is 3.14. D is how much? 150 mm. Hello?
Yes, sir.
But you need to find V in meter, na? Therefore, you will do 150 by 1000 because in 1 meter there are 1000 mm, na?
Yes, sir.
Because you need to find in meter, but it is given in mm. So you should divide by 1000, na, to convert it into meter. Right?
Yes, sir.
And N is how much? 1200. This is per minute. So by 60 by second. To solve it, how much you are getting this? 3.14 into 150. Yeah?
3.786. So,
No, V how much you are getting? Value of V is how much you are getting? You will get this around 9.42 something meter per second. Solve it. Have you got 9.42?
9.48.
Yeah, right. So now it's simple. So power equal to what? FC into V. FC we have got 402 and this is 9.42. So how much this is will get? Just solve this 402 into 9.42. How much we get?
3786.
3786. Right. This we are getting in joule per second. This is watt. This is actually watt. But we want in kilowatt, na? Then we'll divide by 1000.
Yes, sir.
So it will come around 3.78 kilowatt. Right?
Yeah. I was
Yes,
doing
sir.
that answer. 3.78.
Okay. It is fine, na? So
Yes, sir.
what we have done, we need to find the power. So we know power is FC into V, where FC is in Newton, V is in m plus meter per second. So we have other forces. From that we calculated V, FC, and from V calculated pi dn. So pi dn by 60, but we need meter, so we did 150 by 1000. From here we calculated V. So FC into V we got in watt, but we have to find in kilowatt to be divided by 1000. Is it fine?
Yes, sir.
Okay. So we just move to next question. Now see. The rod is subjected to a force 650 Newton. Okay, the force is around given, it is 650 Newton. The Young modulus E is 400 gigapascal. It is 400 gigapascal. The Poisson ratio, which is mu, is 0.2. Right? Cross sectional area, which is A, it is given 120 mm square. Find the magnitude of transfer strain. Transfer strain मतलब epsilon t, right? Hello,
Yes.
can you solve it?
I will try, sir.
Please try. Just use the formula of Poisson ratio. It's very simple. Have you done? Hello.
Sir, not getting the answer.
See, basically you should know what is the formula, right? See, we know कि the mu is equal to what? Lateral strain,
Lateral strain upon transverse strain.
lateral upon longitudinal. Transverse and lateral are same only. Okay.
Yes, sir.
Fine, na? So you need to find the lateral. So you need to find a transverse and lateral are same. है ना? This lateral and transverse are same. So अब this is equal to how much? Mu is how much given? 0.2, which means the lateral strain or transverse strain, anything you can write, transverse strain is 0.2 into the longitudinal strain, right?
Sir.
Now what is longitudinal strain? Strain is what? Stress upon E, na? Sigma is equal to E into strain. We know that, this we know. This is what? Longitudinal strain only. So this is equal to what? Sigma upon E, na? Sigma upon E, right? Hello.
Yes, sir.
Sigma upon E. E also we know. E also we know this much, 4 gigapascal. We just need to
Yes,
find. We just need to find sigma, and sigma is what? Force upon area. Just
Yes, sir.
put to 0.2 into sigma is equal to force upon area into E. Right?
Yes, sir.
Just solve it now. 0.2 into force is how much? 650 Newton. Area is 1, but it is in mm square. To convert it into meter, to 120 into 1 mm is 10 to the power minus 3. It will be about 10 to the power minus 6. Right?
Yes, sir.
Into E is gigapascal. So 400 into 10 to the
Plus
power
6.
9.
Plus
9 na?
Oh, sorry, 9. Yes, sir. Mega 6. Yes.
है ना? It is gigapascal.
Yes, sir. 9.
Okay, just solve it. How much it is coming, say? Just solve this.
So 1.2 into 10 raised to minus 6.
How much?
1.203 into 10 raised to power minus 6.
Actually, I am getting 2.7 10 to the power minus 6. This I am getting. Please check. Some calculation mistake
Yes,
has.
sir. Yes,
Yes,
sir.
sir.
Yes, sir. Yes, sir.
It's right.
Yes, sir. Right.
Okay. Everyone got this, na?
Yes, sir. 2.7 into 10 raised to minus 6.
You understood, na? How we got?
Yes, sir.
Okay. Then can we move to next question?
Yes, sir.
Okay. So now it's given our two component cantilever beam. So we should know now this is the cantilever method. We have learned, na?
Yes, sir.
The cross section of the beam is 6 into 6. Now it is 6 into 6. 6 into 6. Right? है ना? And E is given 300 gigapascal. And the strain gauges are 110 mm away. मतलब the L is given 110 mm. The strain now the force is around 200 Newton. It is telling the strain caused because of this force. We know in cantilever method what is the value of strain? Anyone knows? Hello? 6 into F into L upon
EB H square.
EBS square. Right? Now here B and H are same only. Because both 6 are given, na? This is B and this is H. Here both values equal to 6. So B equal to H equal to 6, right? So we can write 6 FL upon EB or EH cube. Fine?
Yes, sir.
Now solve it just. Ki 6 F is how much? 200 Newton. L is 110 mm. Then you will have to divide by 1000. So 110 you need to divide by 1000 here because convert into meter, na? Into E is how much? 300 into 10 to the power 9 because in gigapascal. Into H square. H is how much? 6. So 6 into 10 to the power minus 3 cube. Right? I am converting everything
Yes, sir.
into meter. Just solve it now. You just need to take care while conversion of unit. Rest is very easy. See this, the L which is there, na, the strain gauges are itna minute away. So that is the length between the strain gauges. So that is F into L. You calculate this first, then I'll discuss one more thing about this.
Why 110 is not in meter?
Why? It is in meter, na?
No, millimeter.
110 by 1000 I have done, na, downside.
Oh, yeah, yeah.
Sir, 2.03 into 10 raised to minus 3.
how much?
2.03 into 10 raised to minus 3.
Right, 2.04 something, 10 to the power minus 3. Fine. Is the answer. Sometimes this F into L is what? This is the moment, na? F into L is a moment. Torque moment you have heard, na? Bending moment something.
Yes, sir.
So this sometimes F and L will not be given. Sometimes it will be given the moment value. So instead of FL you have to directly use 6 into M upon EBH square. Right? Don't get confused. This M is only F into L. Right?
Yes, sir.
So sometimes if F and L are not given, directly value of moment is given Newton meter. Just use that value. Don't get confused. Fine.
Yes, sir.
Can we go to next question?
Yes, sir.
Okay. The next question is that now see, now you have to read thin ring produced means it is that thin type force calculation, na, ring type, and it is given at
Yes, sir.
90 degree only. So you know what is the strain value at 90 degree? We know, na. E at 9. Wait, sorry. E, 1 second. E at 90 degree is equal to plus
Plus or
minus
minus 1.09
1.09 into
FR
FR
EBT
upon
square.
EBT square, na?
Yes, sir.
This is a formula. So what all we have? We have this strain value already. We have this value is equal to 3 into the power minus 5. Right? Now
Yes, sir.
this now what it is saying, read properly. To increase the sensitivity, the diameter of the thin ring has been increased by 2 times. This is radius, na?
Yes, sir.
So now if diameter is increased means radius also increased 2 times. So for example, this is R1. Say this is R1, this is B1, this is T1. है ना? Now they are saying the diameter 2 is twice of diameter 1. Right? Hello?
Yes, sir.
This means this is 2 times of R2 into 2 into
Yes,
2
sir.
times of R1. This 2 cancel means R2 is also 2 times of R1. First step. Second, the width is reduced by half. Means this width is B na. So B2 is half of B1.
1/2
Half of B1. B2 is half of B1. Okay, this is our 1, this is 2, and thickness is reduced by a factor of 3. Means T2 is 1/3 of T1.
Okay, sir.
Right? Right na?
Yes, sir.
So now what you do, you put this value here. Okay. So our you have written this. So I'll just
Wait, sir.
Acha, you're writing.
Yes, sir.
Wait, I'll use a different slide for this. Yeah. Can I proceed?
Yes, sir. Done.
Okay. Now
Yes, sir.
just what it has asking, the new strain will be. Fine. Na? The new strain will be. So now new strain means E2. So E2 is same formula, plus minus 1.09. How much? F into R upon
EBT square.
EBT square. But here R will be R2 and B2 and T2, right?
Yes, sir.
So this can be written as plus minus 1.09 0.09. See, now R2 is how much? Twice of R1?
Yes, sir.
Twice of R1 upon E is same. B2 is how much? Half of B1. And T2 is how much? 1 by 3 times of T1. Fine? Hello?
Yes, sir.
So just solve it. It becomes plus minus 1.09. You take this upwards. So 3 square will become 9. And this will become 2. So 9 into 2, 18. 18 to 36, right?
Yes, sir.
So it will become 2 into 9 into 2, which is 36 into FR1 upon E into B1 into T1 square. So it will become 36 into E1. Rest is E1 only.
Yes, sir.
So 36 into E1. What about the value of E1? E1 was 3 into 10 to the power minus 5.
10 to the minus 5.
3 into 10 to the power minus 5. So it will value will become 108 10 to the power minus 5.
Yes, sir.
This is the answer. It's okay, na?
Yes, sir.
Just you need to play with the values, nothing else. Can we move forward? Hello.
Yes, sir. Sir,
Yes.
sir, what about the plus minus 1.09?
Nee, it's not required, na, because including that for plus minus 1, the value of E1 is given, na.
Yeah.
It is
Yes,
including this value. This we need to use this value only,
sir. Yes, sir.
right? Okay, I'm moving to next question, huh? Okay. Now the length of a cantilever tool. Now it's a cantilever tool. Is changed to 1/4 of the original length for the same cutting force. The percentage reduction in the deflection. It's all about deflection. This is this case. This is the cantilever, right? I have taught if some force is applied and some length is there, it will deflect. So how much it will deflect? Delta, which is equal to FL cube by 3EI. Right?
Yes, sir.
It is asking ki if the length of the tool is changed to 1/4, then for the same cutting force, the percentage reduction in the deflection. So if delta 1 is equal to FL1 cube upon 3EI, right?
Yes, sir.
है ना? And now the L2 is 1/4 of L1.
Yes, sir.
Right? Hello?
Yes, sir. Yes, sir.
1 second, na? Just 1 second. So now if L2 is 1/4 of L1, then delta 2 will how it will become? F into L2. L2 is 1/4, na? So L1 by 4 cube upon 3EI.
Yes, sir.
It will become F L1 cube upon 4 cube is how much? 64. 64 into 3EI. This
Yes,
means
sir.
delta 2 is how much? Delta 1 by 64.
Yes.
Delta 2. So it has asked what it is as the percentage reduction in deflection. This means the percentage reduction in deflection is delta 1 minus delta 2 upon delta 1. Change in deflection upon original deflection. है ना? Into 100 for percentage. So delta 1 is how much? 64 times of delta 2 minus delta 2 upon 64 times of delta 2, which is equal to 63 upon 64 into 100. Fine?
Yes, sir.
Just solve it. Answer is 63 into 64 into 100. Just solve it. What is the answer coming? You might be getting 98.4 something percent.
Yes, sir. 98.43.
Right? This you understood now what we have to do?
Yes, sir.
Any doubt in this?
No, sir.
Okay, so we are moving to the final question, the last question for this session. So, see, the gauge factor for the gauge is 3. G is given to be 3. Right? The strain is applied when strain value is given 3 into 10 to the power minus 5. The change in resistance is, which means the del R, the change is given is del R 0.75 10 to the power minus 3. Then what is the value of R? R value. Can you find this? Just apply the formula.
Yes, sir.
Please solve it. Please solve it.
Sir, 8.333.
8.33c. So how we will do that? We know gauge factor is equal to
Formula.
del R by R upon epsilon.
E. Yeah.
And then which is equal to 3 equal to del R is how much? 0.75 10 to the power minus 3 upon R into epsilon is 3 to 10 to the power minus 5. So R is coming around 8.33 ohm. Right?
Yes, sir.
So this is the answer. Everyone got it, na? Hello.
Yes, sir.
So our today practice session, everything is completed. So before leaving, if you have any doubt in the theory part or in this practice session, please let me know. Any doubt, you can check once what we have gone through today, or any previous doubt also if you are having, we can discuss. We have still 5 minutes.
Sir, no doubt about today's session. Sir, one question is how will be the exam pattern?
See exactly what would be the exam pattern, I cannot tell you because I also don't know, but according to my experience, it would be a mix of numericals, some theory and some derivations maybe also, but mostly you will get the numericals.
Sir, that means it is a MCQ type questions.
That I can
Okay, we have to write.
that I cannot tell because maybe it's online only. It's online only, right?
Yes, sir.
Then it will mainly MCQ only.
Because sir, assignments are only MCQ, sir. That
So mostly 90% it will be MCQs only, because if online exams cannot ask this. I think the derivation and all. But
Yes, sir.
it may be, I think, time based, or maybe you will be given some time that exactly I'm not sure of.
Yes, sir.
Okay.
During last live session, Dixit sir told that it will be MCQ.
It will be MCQ. Then it will be MCQ.
Okay, sir.
Yeah, because he will only decide na what questions to be set. I think just if before exam, what questions we are solving and what assignments you are having, just go through that thoroughly. There will be no issue for you in the exam.
Because there are a lot of materials. It is
You
difficult to remember all
see,
the formulas.
just keep a piece of paper, write each and every formulas in one or two paper. Just read those formulas before exam, and you will be okay. Because it's all about the formulas only. There is no much concept required.
Okay.
Yeah. So
Okay.
is it okay? We'll meet next week for the other session.
Yes, sir.
Hope you like it, and I'll upload this video on YouTube. So you have any doubt, you can just check it.
Yes, sir.
Okay.
Yes, sir.
Okay then. Thank you everyone. Have a
Yeah.
nice day.
Thank you, sir.
Bye.
Yeah.
Thank you, sir. Bye, sir.
हाँ.